In this video, we're going to learn about separable differential equations. A separable first-order differential equation is one that can be written in the form dy over dx is equal to f of x times g of y. And it is important to note that that relationship there is multiplication, but multiplication can be transformed into division and vice versa. So it is also possible that you would see division here, and we could easily write that as multiplying by a fraction. So if this is true, if we can write our differential equation in this format, then we can solve that differential equation by separating the x and y variables from one another. We're going to use multiplication and division to isolate the x and y variables onto separate sides of the equation. That includes the dy dx. We want those differentials there separated as well. So I'm going to multiply the dx from the left over to the right, and I'm going to divide the g of y from the right over to the left. And once we have our variables separated, this is what it's going to look like. And we can solve this differential equation by just integrating. So before we jump into solving, let's first look at a few different differential equations and try to decide if they are separable differential equations or if they are not separable. For our first example, we want to decide if the differential equation dy over dx equals 4xy squared is a separable differential equation. If we can write this differential equation as a product of a function of x and y, then we should be able to separate it. Now, we're not going to be solving it right now. We just want to know if this is possible. It is possible to write our differential equation as some function with only x's times another function with only y's. And I just insert the parentheses so it's very obvious what our two pieces are. So this one is a definite yes. It is separable. Our next differential equation is dy over dx is equal to negative e to the xy squared, all divided by 3x. The divided by 3x won't be an issue because we could, if we needed to, write that as multiplication. But the piece that's jumping out at me right now that makes me concerned as to whether or not we might be able to separate the x's and the y's is that exponential piece. So let's think about how we would separate factors in an exponent. What does it mean when there is multiplication in your exponent? That means that you have one power raised to another power. So one way that we can rewrite that is the negative of e to the x all raised to the y squared. It would still be all over 3x. And there really is no rule on which one is inside or outside there. We could also write this as negative e to the y squared all to the x over 3x. Those x's do not cancel. One of them is in the exponent and one of them is not. One of them is a factor. But it doesn't look to me like we are going to be able to separate those, the y squared and the x. We are not going to be able to write this as just some function of x times some other function of y. We really are not ever going to be able to separate those two pieces into separate factors. So the second one here is not separable. We would have to learn a different way to solve this one. And we're going to take a look at one more here, and this one is very different when we first look at it. It says x squared y dx minus y squared minus 1 dy equals 0. So this one is not presented to us in the way that the definition for a separable differential equation should typically be set up. So one option you have is to use algebra to move all the terms and factors around to see if you get it to match up with the definition we had, that formula we had in the definition here. See if we can use algebra to transform it into dy over dx equals f of x times g of y. So we're got to play with this one a little bit. I'm going to start by adding this entire term over to the right. So I've got x squared y dx equals y squared minus 1 dy. And we want to see dy over dx, so I'm going to divide my dx over, and we want the dy dx by itself, so I'm going to divide the y squared minus 1 over. And what we get here, and I'm going to switch who's on each side, which algebraically is perfectly legal. We've got dy dx equals x squared y over y squared minus 1. So the left-hand side looks good. We want to figure out if we can separate the x's and the y's into a multiplication problem, and we can here. We are allowed to pull that x squared out of the numerator and write it as a multiplication off to the side, and then leave all the rest of the terms with y's there in the fraction. And we are able to write this one in terms of a product between a function of x and a function of y. So yes, this one is separable, and you might have seen that a few steps back. I just wanted to commit to the method I told you I was going to do for this problem. So right from the get-go, I said I was going to try to write it in the format that we have in the definition for separable. All right, so now that we know how to figure out whether a differential equation is separable or not, we want to solve some of these. So right now, all of these will be separable. And we want to use the method that we've just learned of separating the x and y variables to opposite sides of the equation and then using integration. The first differential equation we're going to try to solve is dx over dt is equal to 4x over t squared. Now, I'm not going to go through the process of showing that this is separable. And on a homework or on a test, you may just, if you have a suspicion that it might be, if you see a lot of multiplication and division and you don't really see any addition or subtraction, there's a good chance that it will be separable, and you can just go ahead and try to make it as such. So in order to solve this one, we always want to take the differential that's in the denominator and multiply it over, because in order for us to use those differentials inside of an integral, they have to be multiplied by whatever our integrand is. So we always want to multiply that one over. That tells me I want my dx's on the left. I want all of my x's on the left, and I want all of my t's on the right. Coefficients don't have to be moved, and I actually suggest that you don't move them. So I'm not going to move the 4. I am going to leave the 4t squared right where it is. And in order to separate, I am just going to divide both sides by x. So I've got 1 over x dx is equal to 4 over t squared dt. All of the terms or factors that have x's are on the left, and all the factors that have t's are on the right. So now we can solve by integrating. The antiderivative of 1 over x with respect to x is natural log of absolute value of x. And we don't need to write our plus c arbitrary constant because we're doing two indefinite integrals and they could both have arbitrary constants. We're just going to pretend like we've combined them together onto the side with the independent variable. So no arbitrary constant here on the dependent variable side. For the antiderivative of 4 over t squared, we're going to want to bring the t squared up to the numerator so that we could do power rule. So I'm going to rewrite this as 4t to the negative 2. And when we work our power rule for integration there, we're going to add 1 to the exponent and then divide by the new exponent, which is going to give us negative 4t to the negative 1. And on this side, we'll put our plus c. So right now we've got natural log absolute value of x is equal to negative 4t to the negative 1 plus c. I'm glad we came across this type of problem so quickly because this is a type of solving that we're going to have to do quite a bit. X is our dependent variable, and whenever possible, we would like our final answer in explicit form. So we want to isolate that x value there. So we need to do some operation that will cancel out a natural log, which is going to be a power of e. So we're going to raise both sides of the equation to the power of e, and we're left with x is equal to e, and I'm going to write that t to the negative 1 as a fraction. That whole entire side goes in the exponent. The whole entire side goes in the exponent. But when you have addition in your exponent, that technically means multiplication of two exponential values that have the same base. It's one of our laws of exponents, but done in reverse so we can pull them apart. The e to the c here, since e is just a constant and c is just a constant, and technically an unknown constant, we can just think of that entire factor right there as an entire multiply by c. And we're going to see this quite a bit when we get to exponential growth and decay applications. So what we've got for our final general solution is x equals c times e to the negative 4 divided by t. That is the general solution for our differential equation. For our next example, we want to find the general solution for the differential equation t cubed y squared dt plus t to the 4th y to the negative 6 dy equals 0. Well, so far the only way we know how to solve differential equations is by separating. So that's what we're going to need to try to do here. See if we can get all of the y's on one side and all of the t's on the other side. Because it is written in this fashion, it's not obvious necessarily which variable is the dependent and which is the independent. So one rule of thumb you can always use if you're not told otherwise: the letter that is farther along in the alphabet is going to be, go ahead and use that as your dependent variable. So the reason is because y is farther along in the alphabet than t is. So I would just let y be the dependent variable and t be the independent variable. So what that means is, if possible, at the end of this problem, I would like to solve for y if I can. The typical format we would see our answer in is y equals something. So I'm going to go ahead and leave the y terms on the left-hand side, and I'm going to try to move the t terms over to the right-hand side. So I am going to subtract this entire term from the left over to the right. And when we do that, we get t to the 4th, y to the negative 6, the dy, equals negative t cubed y squared dt. So we've still got a mix of t's and y's on both sides, but it's all multiplication. So we could just use division to get them separated. I want to leave the dy and the dt where they are, because our next step after this is going to be integration, and the dy dt can't be in a denominator when we use it in that integration. So leave them right where they are. That means I want all my y's on the left, so I'm going to divide this side, or both sides, by t to the 4th and y squared. What we have now is y to the negative 8 dy is equal to negative 1 over t dt. And we'll integrate both sides. And get negative 1/7 y to the negative 7 is equal to negative natural log absolute value of t plus c. And since our exponent on our dependent variable here of y is odd, we could technically solve for y if we wanted to. I don't think it's going to make our answer look any better. But if you're interested, the first thing I would do is multiply both sides by negative 7. And you do not have to apply that to the constant for the same reasoning in our last problem when we had e to the c we just kept it as a c. We didn't really need the e because it was a constant. So we really don't need to apply that -7 to the c because it would still be some arbitrary constant. So if we solved, we get y to the -7 equals 7 natural log absolute value of t plus c. And -7 means y to the 7th flipped. So the next step I'm going to do is flip it back up by flipping this whole side and then take the 7th root, which is really, really ugly. So that's why I said I don't think solving for y here is going to make it look any nicer. But it is possible to do so if we were asked to. Y is equal to the 7th root of 1 divided by 7 natural log absolute value of t plus c. And there really is no simplifying we could do there. We're going to solve a couple of initial value problems next. There are some problems that we are going to see where we're given some additional information about the solution. And that additional information is going to be a specific ordered pair that we know should satisfy our solution. We call those initial solutions because in real life problems that we would use differential equations for, we only have control over the initial setup of whatever the experiment is we're doing. We don't have much control, and we can't measure necessarily with perfect accuracy anything that happens after that. So it's very common that we'll be given a differential equation to solve, but we would also be given an initial condition for that solution function. And we would be told y of 0 is equal to some value, which just happens to be the initial y value. This is called a particular solution. And we don't solve for it differently. All we do is we continue on from our general solution. So when calculating a particular solution, all we're really doing is taking our general solution and solving for and replacing the arbitrary constant with whatever value we find satisfies this ordered pair that we're given. The ordered pair is often represented or presented to us as a function value, such as y of 0 equals 5. But that means the exact same thing as the solution function passing through the point 0, 5. So they're giving us an x value of 0, a y value of 5. So be careful if you're not used to that notation. The y value is not the one that's immediately next to it. It's the one on the opposite side. So in order to solve and replace that arbitrary constant, what we're going to do is we're going to take this x value and this y value that we're given, and we're going to plug it into our general solution. And when we do so, the only unknown value in that general solution should be the c value. So we should be able to solve for it. But be very careful. The c value is not the answer. If we're being asked to find a particular solution, then we're expected to answer the problem with an equation that has no arbitrary constants. That is what a particular solution looks like. We're still giving an equation, it just doesn't have a plus c. We've been able to calculate that c value, and we have replaced that c value. So we're going to look at a couple more separable differential equations, but these ones we will be given initial values, so that what we're really trying to do is solve for a particular solution. Both sets of directions mean the same thing. You would be expected to do the exact same thing. So I'm going to write those here as well. It could say solve each initial value problem or solve for the particular solution. For our first initial value problem, we are asked to find the particular solution for the differential equation dy over dt is equal to 2t cosine squared y. And we know that y of 0 is equal to pi over 4. So this is our initial condition. we're going to just hold on to this piece until the end. We still start this problem the exact same way, where our first goal here is to get the t's and the y's separated. So I'm going to multiply my dt over to the right, and I'm going to divide my cosine squared over to the left. Our next step is going to be to integrate, and I am not real happy with the format my y's are in, so I'm just going to rewrite that first as secant squared dy. Cosine squared in the denominator is the exact same thing as secant squared. That one for me is going to be easier to integrate. It's more recognizable because I remember the antiderivative for secant squared is tangent, and that is my dependent variable, so I'm not going to include a plus c. I'm going to include the plus c on the independent side, which is the t value. So the antiderivative for 2t is t squared and plus our arbitrary constant. Because this is an initial value problem, I'm not going to end this problem here with solving for y by doing tangent inverse. I'm going to use my t and my y value and plug them in now while I see operations that are more familiar to me. So remember, the y value is on the opposite side. What this is telling me is that t is equal to 0 and y is equal to pi over 4. So when t is 0, y is pi over 4. So the only unknown value there is the c. We can solve for the c. Tangent of pi over 4 is equal to 1. 0 squared is equal to 0 plus c is c. So the c value is 1. So we've got tangent of y is equal to t squared plus 1. And if we want to, we could solve here for y by doing tan inverse of both sides. Here they'll cancel, and on the other side it'll stay. We'll have y is equal to tan inverse of t squared plus 1. Beautiful. It's still an equation for the answer. It just has no arbitrary constant. We're able to solve for the c value and replace it. And let's look at one more initial value problem. For this one, we have dy over dx is equal to 3x plus yx, and y of 0 is equal to negative 3 halves. So again, we're going to hold on to this guy for later. And right now we just want to start by finding our general solution. So this has to be separable. The only way that we've learned so far is by separating. But I see addition here, and one of the terms has both an x and a y. So it might be difficult to separate here without using addition and subtraction, which is typically not legal. But what I suggest you do, since both of these terms have an x, we should factor it out. And that's how you'll see that this guy is separable. He can be written as a function of x times a function of y. So let's go ahead and separate these guys using some multiplication and division. We're going to get 1 over 3 plus y dy is equal to x dx. And to solve, we want to integrate. We get natural log absolute value of 3 plus y is equal to 1/2 x squared plus c. I'm going to go ahead and solve this for y by first getting rid of that natural log. And remember earlier when we saw that plus c up in the exponential, it came out front as a multiplication. So now I have 3 plus y is equal to c e to the 1/2 x squared. And then just subtract that 3 over, and we have a general solution here. Our general solution is y is equal to c times e to the power of 1/2 times x squared, and then minus 3. We were asked to solve the initial value problem, which is the same as finding a particular solution. So we need to solve for that c value, knowing that when we plug 0 in for x, we should get back negative 3 halves for y. So that's the next thing we need to do is plug in those values. When we have 0 for x, we should get back -3/2 for y. 0 squared is 0, and then times 1/2 is 0. But be careful, because e to the 0 is equal to 1. And c times 1 is just c. So we've got -3/2 is equal to c minus 3. We'll just add that 3 value over, and we get c is +3/2. Be careful, that is not your answer. We're looking for a particular solution. So now what we want to do is rewrite our general solution, but replace the c value. So y is equal to 3/2 e to the 1/2 x squared and -3.